Okay, so I've started recording. So hello everyone. Thank you so much for coming. I know it's a little bit earlier in the morning, especially on a Friday, but thank you all for coming to this intro to machine learning lecture series that we'll be starting as part of the INIT AI Guild. Well, it used to be called INIT AI Guild. I don't know what it's called now, but the INIT AI.
Sorry about that.
So my name is Jose, and I'm joined with my co-host, uh,
Joas,
Josh.
hi guys. Sorry about that. Hi guys. My name is Joas. I'm a stats major here at FIU. I guess we'll do the introductions
Yeah,
after. Oh, yeah, there we go. So yeah, that's not really me. That's an AI generated image of me using Flux. It only took like 15 images to train. That was pretty cool. But yeah, I am a stats major here at FIU. I'm a computer science minor. I'm about to graduate in like May if everything goes according to plan. I also work at the AI lab at EC, and I work in doing basically image generative AI research. So like what I've been basically researching is stable diffusion models, flux models. So like Dolly, I don't know if anybody's familiar with that. Yeah, no. So like whatever you guys like ask GPT to generate an image, that's usually stable diffusion. That's what Dolly uses. But yeah, that's about me. I'm very, very passionate about mathematics. Math is like my favorite subject, and I like the combination of using mathematics to basically come up with like images to generate text. I find that world very interesting. Yeah, and then I guess Jose is gonna take over.
yeah. So I'm Jose. I grew up in Miami and recently graduated from FIU with my bachelor's in computer science. During my time at FIU, I was involved in the machine learning community there. And now I live in California working as a software engineer at Google. So our goals for this whole lecture series is we want to take you from assuming that you know nothing about machine learning and give you a roadmap to understand transformers, which is the state of the art right now. We share the roadmap with everyone. I hope everyone has access to the roadmap. Does
Yeah.
everyone have access to the roadmap?
Do you guys have access to the Notion? Yeah, so it's in the Notion. I think if you go to the bottom of the homepage, there should be a link that says like Foundations to AI. And then once you click on that, it's going to give you the full like course and what we expect to cover in this course and what we're going to go over.
Yeah, so on there, exactly, like we'll outline exactly what we're going over for the day and the day that we'll go over it.
Yeah.
And also, we were a little bit late this time around, but we hope to
So have,
give you the presentation like a week in advance and all the things a week in advance so that you have enough time to look over it.
yeah.
Um, did my share just drop?
Yeah, I did.
That's tough, bro.
Things happen.
That's wild. Okay.
There we go.
See it now? Is it back up?
Yeah, it's back up. We're good.
Okay. And so, we're going on this journey together. I know that sounds cliche, but like we're also fellow students. At least I see it that way because we're also learning. And so I don't want to just throw an equation and say like here, like use this because like I don't like it when my professors did that. So we're gonna ask like the questions like why is this relevant? Like why are you learning this? How does this fit into like what we ultimately want to achieve? Because I feel like a lot of times in class, like I don't know, the teacher goes over something and then you've no idea why this is relevant or how this is useful in any capacity. So we want to we don't want to do that. So we want to take like a very intuitive way of learning about this. And so our goal is that we can learn the building blocks of neural networks. And you will see that you can learn building blocks. And then if you learn the building blocks, then making neural networks would be like a Lego set, basically, because all you're doing is putting the building blocks together. And honestly, like when we start actually coding up neural networks, you'll see that it is actually closer to Lego sets than you might expect because all you're doing is like strapping like layers on top of each other and just adding this So you'll see that the analogy is quite close. So I want to give everyone like some time to fill out this interest form, so that now we can get to know your goals. And by the way, I know someone just joined, Jocelyn. Hi, thank you for joining.
Thank you for joining.
You haven't missed much. We just started.
Basically.
You actually joined at a perfect time to fill out the interest form.
Do you want to give them, Jose, like a couple of minutes for them to?
Yeah. I'll give them like 5 minutes.
Yeah, we'll give you 5 minutes. I guess for the people here, you guys can like vocally say, what are your goals in this class? What caught your attention about this class or this lecture series?
They can also. I also want to scan the QR code and fill
Right?
it out.
Yeah, but definitely scan the QR code so we could have it. But yeah, so like, what are you guys interested in ML? Any specific algorithms? Any specific like generative AI? Any specific algorithms itself? Any specific models? If it's the math, if it's the coding side of it that got you interested in this, please let me know. Oh no, they're filling out the forms. There we go. Welcome, Shatoya. I hope I said your name right. Hope I didn't butcher that.
Shatoya, if you're just joining us now, welcome. You came at the perfect time. You haven't really missed much.
Yeah.
You joined at the perfect time to fill out the interest form. So.
Okay, I'll fill it out.
All right, thank you.
Is everyone here joining? Oh, obviously the people are here from FIU, but people that are joining from the link itself, are you guys from FIU?
I'm from FIU, yeah.
Nice. Okay.
Yeah, Jocelyn also.
As well? Thumbs up. Okay.
Yeah, is Edwards also from FIU?
Yeah. He's a stat student at FIU.
Oh, okay, I see.
Yeah, if you guys are done with the forms, in chat, just put a thumbs up or just say done, and then I'll see, I guess, when you guys are done with your forms.
Yeah, I'll give you all like 3 more minutes. Apologies if it's a long form.
I didn't get to look at it. Is it long?
I mean, there's some questions in there that can definitely get you thinking.
Okay.
Yeah. So, like some of the things that I will assume, in this like series and stuff is that you have some background in programming. Doesn't have to be Python specifically, but I think like if you just have like some programming background, like you can pick up some of the Python things rather quickly.
Definitely.
But has anyone here done a little bit of Python before? Okay, perfect. Okay.
Jocelyn's done Python. I know Edward's done Python. Shatoya as well. You guys? Python? Yeah. Okay. How comfortable are you guys with like linear algebra and statistics?
I haven't really taken like linear algebra class, but
Okay.
I guess like basic matrix
Multiplication, like dot products.
Yeah.
Okay.
Yeah, we'll go over that next class. Don't worry.
Okay.
Oh shit! Sorry. I put the wrong emoji. My bad. Oh my.
You good?
Good.
Jordan's there with you in the room?
No,
No?
no. Why did he like type in the Discord chat or
He
something?
filled out the form without this guy. He's a ghost. Okay. Give you a little bit more. Move on.
Are you guys done with the forms? Yeah,
Everyone,
almost. Huh? Oh, before. Oh, okay.
what's that?
We got one person that's almost done, and everybody else is done here.
Okay. All right, let me know when if they're almost done, then I'll give them some time.
We'll do like one more minute.
Okay. Is it cool if I move on?
I think we can start. You're almost done, right?
Yeah.
Yeah. You just submitted it? Okay, we're good to go.
Chilling. Okay, so let's get started then. What is machine learning? Joaz, I can let you take like the next couple slides if you want.
Okay. Well, first of all, I wanted to see if. Okay, I kind of wanted to ask the. Okay. What do you guys know about machine learning? Anyone? There's no right or wrong answers actually. I just want to know what you guys think. You obviously took a course in machine learning. Okay, it's used to make predictions. You guys can answer it in chat as well.
I guess so. Predictions kind of like supervised, unsupervised.
Oh, okay. You know about the different types of learning, and you?
I don't know. I haven't defined it, but I know it's the difference between supervised and unsupervised.
Okay. Okay. All right. Okay. I guess Jose, we can continue.
Okay.
For the
For anyone joining us now, I guess I'll send you. Whoops, I was gonna send you this thing. You can quickly scan this and fill it out later. Anyways.
Welcome, Amy.
Hello.
Hello.
You're not missing much. We're just getting started.
We're just getting started. Was she able to get the form? The link for the form?
You able to scan this?
Yeah, scan that and then fill it out. Yeah.
You can fill out later.
I got it.
Okay, sounds good. And then we're also on the roadmap. I'll have the links to all the presentations, and I can send it afterwards as well, which will have everything.
Okay. All right. So the landscape of machine learning, we have unsupervised learning, supervised learning, and reinforcement learning. You can say that machine learning is a subset of artificial intelligence, or you can say that I think back in the day, artificial machine learning came first. So you could even think of artificial intelligence as a subset of AI. It's kind of interchangeable. Okay, there we go. This is a nice like meme. If you're a stats major, you'll realize how much of like statistics overlap there is with machine learning and with AI. I don't think you can't really do much of machine learning or artificial intelligence without statistics. So supervised learning has to do with labeled data. Has anybody here ever worked with supervised learning before? Yeah.
It was like a simple like house price.
That's the famous house price.
Problem: house prices.
That's good. That's gonna be the example that we're gonna use, but we're gonna try to pick up a different example, but I guess we didn't get to.
I'll make less cliche like subjects going forward, but yeah.
That is the most cliche like problem to do. It's even like a problem that we did in the linear, like I think it was the first problem that we did in linear regression for the stats class in FIU. So supervised learning has to do with labeled data. So house prices. Another famous like data set is like the iris data set, which is this data set about like flowers and their length and the width of the sepals, so you can like predict things. That's another famous data set that they have for that. And then you have like unsupervised learning, where you don't have labels for these data. One of the most like common unsupervised learning in machine learning algorithms, if I'm not mistaken, is like clustering. So you're not labeling the data. Yeah, and it's just all about finding like hidden patterns. And then we have reinforcement learning, which is all via rewards. We're gonna get more deeper into reinforcement learning when we get into deep learning and artificial intelligence. The math of that is amazing. And just the role of neural networks. So you'll notice that the most important, I don't want to say the most important, but probably the most famous machine learning algorithm is probably linear regression. And you'll realize when we get into AI, to neural network, and I think we have it in one of the slides, is that in most neurons, they have like their own linear regression happening in that specific neuron. So machine learning is very important to neural network. And then they're basically used for, so neural networks are used for finding like very complex patterns. So like, for example, like in object detection and image classification, you'll send in an image. And if you can think about the complex representation of that image in pixel format and the relationship with those pixels, a neural net captures that relationship to tell you, whether this is like a cat or a dog. It helps classify or object detect that image. Okay, let's continue. I don't know if you want to add something to that slide, Jose.
No, I think it's fine.
We're good? Okay. So how neural networks fit in the ML landscape? Traditional ML models, decision trees, support vector machine, logistic regression, work well on structured data. Neural networks shine on things like image recognition, object detection, image segmentation, natural language processing, and image generation. And then for like autonomous systems as well. Anybody familiar with any neural network or any neural network models? In fact, we use this for our homeworks all the time. There you go, ChatGPT.
GPT.
Yeah.
ChatGPT.
Yeah.
ChatGPT.
It totally didn't help make this presentation. Anyway,
For real.
or the corresponding code for this presentation. Anyways,
Definitely.
I use Claude, not GPT. Yeah, right. Anyways,
Google guy using Claude, of course. All right, so
oops.
there we go. We could go back.
Okay.
So deep learning is a subset of machine learning, which relies on deep neural networks for highly complex tasks. So basically, a nice little visual representation for you guys to have is that you have AI, then you have ML, then you get into even more specific, then you have deep learning, and then you have neural networks. Very, very, very famous in image recognition. If I remember clearly, the first unit that was used for stable diffusion was used for segmentation on like this like medical research paper, if I remember clearly. I think that's where the research was from. Another famous, didn't somebody win who was the people that won the Nobel Prize for the machine learning model or the AI model that was like for protein folding? That's what it was, right, Jose?
Yeah.
Yeah, that was another famous application. Also like AlphaGo. Does anybody know about that? AlphaGo, they beat like the chess master, right? If I remember clearly, that AI algorithm. But yeah, let's continue. And then this is nice, a pretty good like representation of how they all interchange with each other and how one's part of the other. In deep learning, you have things like CNNs. They're probably like one of the most famous networks there is, having to do with convolutions. And then you have generative AI. In generative AI, you have GANs, LLMs, and that's what GPT is. Uses LLMs. Let's continue.
By the way, stay close to the mic so that.
Oh, it goes away when I walk. Okay, my bad.
Yeah.
All right, and these are some memes to get familiar with. Once you learn more about AI and you get more into AI, you'll definitely get to know Andrew Ng, the Professor Andrew Ng. So
That was gonna make a lot more sense next class.
definitely.
One.
Has anybody taken a course with Andrew Ng before? No? Okay.
His Coursera course is actually really good.
Jocelyn has. Okay, nice. Oh, and Javi's here. Yo, what's up?
Yeah.
Okay, machine learning. Okay, so machine learning fundamentals. I think we kind of went over the
Yeah.
supervised learning. Just so in machine learning, one of the things that we didn't get to, like, I think we'll talk about this later, but like, you want to try your best to see if you can solve your problems without AI and ML. If you can solve your problems without AI and ML, that would be very useful because AI and ML require data. Some of them require structured data, some of them require labeled data, and that's very like labor intensive and computationally expensive as well.
Yeah.
But yeah, so the common like workflow for you to have is that you'll gather data, you'll clean the data, which basically you pre-process the data, you choose a model, you choose your training data to use for that model, you choose your validation data set that we're going to use as well, and then your test data for the ML model. Then you get into prediction and then evaluation and refinement. Yeah.
Yeah. So I think it's definitely maybe on the next slide, but you want to pick the right tool for the job. You don't just want to like, throw right now, everything looks like a nail when you have a hammer, that is AI. So, you want to throw it at everything, but yeah, part of learning about different types of models is also to know like which model can help best in what situation. So like if labels aren't something that you have, then maybe like unsupervised learning might be a better way to go than supervised learning. So it really depends on your task.
Definitely. And then I've seen like in like Discord and in certain like Medium blogs about how like certain companies have tried to like implement AI into their business plan, and those business plans like probably went down under because a lot of those people don't understand how like expensive it is to have an AI feature or like some sort of AI feature to have or some sort of AI product to have or to implement that in your system. It costs a lot of money. So that's why I always say like you have to think about the problem. You have to see if you actually need AI and ML. If you can solve it with basic statistics or just old statistics, you just solve it that way as well. So
I added a little diagram as well, on what that workflow looks like. So like before you can even like train your model, you need to know like, okay, like what data am I going to use to train this model? If you don't have any data to train the model, you can't train the model. Then obviously you gotta like code up your model, you train it, evaluate it, and then you tune it. So like if you're training it and then you see like, well, my model's not doing so well, then you need to go back and fix that in some way. Then like you deploy your model, get predictions, monitor the ongoing predictions, and then you manage your versions from there.
Oh, and one more thing to add before, like a lot of the times in the actual workforce, I've spoken to a lot of like data scientists. They end up sometimes having the role of a data engineer as well, because a lot of times you don't end up getting that data clean. I don't know if anyone here has done like some sort of machine learning project. I've done a couple, and a lot of the times you don't get the data. A lot of times, sometimes you have to web scrape the data. Sometimes that data comes extremely messy, and yeah, like. So yeah, and then I don't know if you guys know about like that famous. I think there was like a lawsuit between like Reddit and like OpenAI.
It's been
Okay, so machine learning fundamentals. So
blurry.
Huh?
No, this one's super blurry. Oh
shit. Oops. Yeah. So yeah, you have machine learning fundamentals. You have regression, classification, and clustering. And here in the top right, you have a picture of what regression is. And it's all about basically fitting a line over your data to explain the variability of the data, to make predictions on the data. This is a very famous machine learning algorithm called the logistic regression, which is commonly used in classification. And in there, that's an example of binary classification. Anybody want to take a guess at what that third one is? The ones with the colors.
I mean,
Clustering. There you go, clustering. You overthought it, bro. You overthought it. It's clustering. I guess we can continue.
Yeah.
Okay, yeah, and so we spoke about this already, but some examples of regression. We have the house price prediction. You could do stock market predictions. You could do weather forecasting. And for classification, one of the most famous examples is whether an email is spam or not. Yeah, so you guys know that a lot of your, I don't know if you guys knew this, but a lot of your like email services like Gmail, they use this type of AI feature to guess whether something is spam or not, right? You have sentiment analysis. Anybody know about what that is? Yes, analysis. Okay. And then and fraud detection. Some unsupervised learning examples. You have customer segmentation, anomaly detection, Igman segmentation. Has anyone here ever played with any of the YOLO models? Messed around with it? Okay, so the YOLO models are very famous for their object detection and their Igman segmentation.
We'll look at them more in depth when we get to convolutional neural networks and computer vision.
Yeah.
But yeah.
My favorite version of AI, by the way. So just a heads up. It's my favorite.
Nice.
Okay. And then now we're gonna get into linear regression.
So yeah, now linear regression. I hope we didn't bore you too much with the details. Now we'll get to the fun stuff. Yeah. So Joe has made this nice visualization. So in linear regression, as you saw, you have a set of data points and you want the line of best fit. So why would you want a line of best fit through like random data points? Can anyone tell me why we might want to do that? Oh no, it doesn't loop. Anyone?
And amongst the data.
Jordan says to find a consistent trend among the data.
Yeah. So you'll see like a trend in machine learning is you just want to gather patterns from the data. In fact, the reason neural networks are so useful is because they find those patterns independently without much like programmatic things. So in linear regression, like you learn it because you can start to see a lot of like the core foundation of things of machine learning early on with a simple example. So in this case, like we just have like a random set of data points and we want to know like some sort of relationship or pattern that we can see from there. So you can see that illustrated here. And then we'll get to see how you optimize for how to best fit the model and things like that.
Yeah.
Dude, I'm in like a continuous loop.
It doesn't let you get out for the next step?
Hold up.
Really?
Hold up.
I think you're gonna have to like exit.
I got it.
Sorry about that.
Right.
That's weird.
No, good. So introduction to simple linear regression. So again, like our first ML algorithm that we're gonna learn about is linear regression, which is really a simple model that just tries to answer the question, how can I use X to predict Y, or a relationship between X and Y, where X is the given information that you have and Y is what you want to know. So you can see that this is supervised learning because, for example, when you're training a model, you have some previous examples that you're looking at or some existing examples, and you're looking, you know what the true value is. You know what the Y that correlates to the X's are, right? So like these data points. Again, the classic example is you want to sell your house and you want to know how much you can sell it for. Although with current interest rates, good luck. Yeah, so let's say like you have this data points, you can fit a line through that, and then let's say that your house has 5 bedrooms. Well, I don't see any other data points that have 5 on there, but maybe I can make a prediction to say, okay, I can sell my house for like 315K or something. So I think you can start to see like why a model like this could be useful, and it's extensible. It's extendable in many different domains. So mathematics of linear regression. Joe's just got so happy right now. So I mean, does this remind anyone of anything? Like, what does this look like to you?
From high school or middle school? Anybody have a guess? You know this, huh? The equation of a line, right?
Y equals mx plus b.
What does the W1 like remind you of?
Yeah, what would this be?
Huh? Slope, right?
Yeah, this is slope, and this is the y-intercept.
Yeah, that's your exactly.
I'm labeling it like this right now, and you might think this looks a little weird. Why not just and we'll use W0 and B interchangeably because B is called a bias. But I'm showing it to you now just because we'll see like this notation going forward a little bit more. But you can see like in a simple model, you just have a line, but you can extend it out to any number of terms. So you can have m number of features. Actually, I should explain what this is. So y is your output variable, which is the target that you're trying to predict.
Yeah.
X is your input variable, which in machine learning, we call them features.
Yes.
So for example, the feature that we saw in the previous example was the number of bedrooms, and the output target variable was the price.
Yep.
And then you have a bias term and this thing like a regression coefficient, but in machine learning, we call them model weights. And so you see that weights will be attached to features, and it's called weights because it'll tell you like how important that feature is in the prediction. So obviously, the higher the weight coefficient here, the more important that feature will be to the output of the model, right? If this weight here was 0 or something very close to 0, then like it's as if that feature just wasn't there. Versus if it's a very high number. So again, it's the weight of how important that feature is. You can expand linear regression to n number of features. And so if we think back to the house prices example, like we only had one feature, the number of bedrooms, but you can easily extend that out to way more features like square footage, number of bathrooms, year the house was built, the neighborhood, if there's attractions nearby. And just showing it to you in like a 3-dimensional example. So say Y is our label. And we have two independent variables here, like two input variables. Or actually, yeah, independent variables. Yeah, I was like, bro, I got confused for a second. See, in 3 dimensions, this looks like a plane. And if the math is already starting to get like kind of funky, don't worry. Essentially, you can see when we had 2 dimensions, it was a line. When we went to 3 dimensions, this looked like a 2D plane. As you go to higher dimensions, obviously I can't plot 4 dimensions for you, but as you start going up in dimensionality, this is the idea that you can have a sort of trend that models your data. And you can, even though you can't go up to 4 dimensions or 5 dimensions, like geometrically that is, you can still represent that in the equation and it will work just fine. So I guess, you know, we do have the question that might seem silly, but how do you find the best line that fits your data? Okay, so I want someone to raise their hand and tell me which is the best line and why is it green? Okay, actually, like in the chat, like if you're in the call, you can just put in the chat which one you think the best one is and why.
He's trolling. It's definitely not green.
Bro, it's green. If you don't say green, I'm sorry. You're incorrect.
Okay, so Jordan says pink.
Pink.
We'll go with blue. Okay, so Toya says pink. Blue. Okay, we got 2 for blue.
Also, how do you know? Like, why pink or blue? Why not like orange? Why not green? Green is fire.
Because the difference of each data point in respect to the pink line, it's relatively balanced.
Yeah, I guess you could also say the green doesn't really capture the trend, the pattern that you see in the data, right? So now, so how do you know that your line fits well, right? So what Jordan was alluding to is if you have a set of data points and you fit a line through them, one way you can know if it captures the data well is to know how far away the line is from the individual data points. So this is called one way to measure this is using a loss function. And a common loss function for regression problems is called MSE, which stands for mean squared error. Because if you look at the equation, like that's exactly what it does. So this y here is your true value, and this y hat is the predicted value. And so you're essentially getting this difference right here, that green line.
Yep.
And you square it. One of the reasons we square it is when you want to penalize errors quite severely, so that the model can learn. And also, if you don't have it squared, you see how this is below the line? This one might be negative and that one might be positive. And
Yep.
if you sum them up, they might cancel each other out. So if you square it, then you can they'll be positive. You can also take the absolute value, and that will also solve that problem. So it just depends. And we want to sum this up for all the data points and then get an average so that we can see more or less how our model's doing.
Yep. And then this is something that we didn't add to the slide, but another way to, like, when you get into different like model selections of linear regression, and you have like multiple like models, one of the things that you're going to want to compare is, well, you're going to compare the MSE as well, but you can also compare their residuals. And the residuals is exactly that same formula without the 1 divided by n. And what you want to compare is like which models have the smallest amount, or like, and that's how you know which model's better than the other. That's another way to check. You can continue. Sorry about that.
So I want to explain this for anyone seeing this notation for the first time. Again, MSE stands for mean squared error. This y sub I right here is the true value. So it's, remember, this is supervised learning. So we actually know, like when we're training the model, we actually know what the right output should have been. And we're trying to get our model predictions closer to the true should have been value. And that's what the y hat is there, which is the model's prediction. So this term in here is the difference between the true value and our predicted value. And so when we square it, we just get the square difference of that. So this here is the Greek letter sigma. And whenever you see this in mathematics, you know this means sum of. So we want to sum all the square differences from I to n, well, from 1 to n. So assuming that we have n number of data points in our data set, we're just going to do that. And the ith data point, well, I symbolizes like the ith data point, and then you would have the ith squared error for that term. And then 1 over n is, again, just getting the average of all of our data points. So I hope that makes sense. Is this the first time for anyone seeing this notation, like with sigma and things like that?
Yep.
I hope it's...
For computer science majors, another way to think of the sigma notation is as a for loop.
It's literally a for loop.
Yeah, you're literally iterating through the size of your observations. So how many observations you have, which is n, and then you're going through every specific one, and then you're subtracting that observed value minus the predicted, and you're squaring it, you're summing that up, and then dividing by your overall n. So yeah.
Yeah, so it's really just a summation. Like you can write this out as like y1 plus y2 plus y3 plus y4, so on and so forth.
Yep.
So again, why is linear regression relevant? I quickly want to like jump forward a little bit and show you why it is that you're learning this. So when we get to neural networks, which will be next class, we'll see how in a neuron, so this is a perceptron, or you can call it a neuron. And so you can start to see these X's with weights on them, which looks very similar to what we were just talking about right now. And you have this bias term, which again, it's what we have. And then you see this equation over here. This is not the regression one that I was just showing you. There's a different one. It's actually, if I go back, it's going to look very similar to this. So again, it's that sum of, so it's the sum of all the weights and feature coefficients. And so what I wanted you to look at is that for neurons, actually, so what they have is they're really just a function, like what you can see here, where you sum up all the weights and the features, and you run it through this function, which is called an activation function. We'll learn about those later. But in fact, this here inside of that function is actually a linear regression model, which I expanded out for you over here. So like, let's say your neuron is a function n of f of z. Again, f is an activation function, but that z in there is actually a linear computation, which is essentially just like a linear regression model. So you'll see how some of these things will start to connect. And virtually all machine learning models are functions that predict y given x. And almost all of them also use a loss function as well in order to measure how well the model is doing. And they're all parametric functions, meaning they're all parameterized. So like the parameters would be the weights of the model, for example, because the way in which you define those parameters will define the way in which your model behaves. And so our objective is going to be, as you are going to see forward, to optimize those parameters such that you have the optimal model behavior. So speaking of optimization, intro to gradient descent. So how do you find the best model parameters, as we were just saying? So let's say you start off with a random set of points, like what we saw before, right? Let's say that you start with a random model, and you already know how to measure how well your model is performing using your loss function, right? So is there a way to work backwards from your loss function to update your model to get it a little bit closer to the pattern you see in the data, so that your model behaves a little bit more optimally each time? And yes, this is exactly what the gradient descent algorithm is for. And this is why we use it in machine learning, that we go through these iterations, tweaking the model slightly in the parameters, such that you get a different model every time, and you can measure to see if your model is doing better. So I quickly want to recap a little bit of calculus right now, because we're about to get into some of the math. So I'll just throw the trigger warning out there. But all my fellow math nerds, Jordan, I know you guys are there. You're getting excited. So derivatives and minimums. Okay, quick question. How many of y'all have taken calculus before? Just
Anyone? Calc 1, Calc 2, Calc 3, all of them?
And
You guys know about derivatives, and I think in Calc 3 is when you get into partial derivatives here. I don't know if they introduced that in Calc 2.
okay, perfect. I mean, everyone. Okay, this is not the first time that y'all are seeing this, basically. Okay.
Well, I mean, I think everybody but David hasn't seen partial derivatives, right? Yeah.
Oh, okay. Yeah, I never took Calc 3. I just kind of learned that on the fly.
All right, anybody in chat, is this the first time seeing this?
No, I mean they've all taken calculus before, so this should be just a quick recap. So we have the power rule, which is essentially if you have x sub n, x to the power of n, then the derivative is you're gonna bring this down, right? And then you're just gonna have n times x to the n minus 1, right? So if you have an example x squared plus 4x plus 1, you have this x squared becomes a 2x, and then this 4x becomes just a 4, right? Because you can see that it's going to be x to the 0, which is just 1, and then you brought down the 1, multiply, so it's just 4, and then the derivative of a constant is just 0, right?
Right.
And then you also have the chain rule, which I hope everyone remembers as well, but it's when you have composite functions, or like a function within a function. And so what you do is you take the derivative of the outside, and then you take the derivative of the inside. So if you have this function 3x squared plus 2x to the 4th power, so this to the 4th, oh, and by the way, I forgot to, there should be a to the 3rd power in here, but I'll get to that. So you do this derivative outside, so this 4 comes down and goes there, and there's supposed to be a to the 3rd power here. Forgot to add that, sorry. And then the derivative of the inside, well, 3x squared just becomes 6x, and then the 2x just becomes a plus 2, right? And so if we want to find the minimum points of a graph, so let's take x squared as a very simple example. Well, for that, you can take the derivative, set it equal to 0, because what does a derivative tell you? Can anyone intuitively tell me what is a derivative?
I know Jordan's gonna tell me. Let me see if somebody else can tell
Yeah.
me. So like,
Jordan immediately goes, I got you.
so right, as you see right there, we have the parabola. If we take the derivative of that, what does that tell us? Okay, okay. Anybody else have a? So if I were to get like the derivative of this, would be this line, right?
Oh, I wish this was interactive so I could show you.
Yeah.
But anyone in the
In the chat.
want to tell me what a derivative is? I'm sorry. I know this is, you might think this is not related to neural networks. You'll see.
Is.
You'll see.
How sensitive, the function is at that one.
How sensitive that function is. Okay, as in like how fast like it increases or okay, okay,
Yeah.
okay.
So I guess the derivative really tells you a couple of things. Two things primarily that we want to know is like a slope. Yes. But then again, what is a slope? A slope is really a rate of change. If I wanted to measure, if you were to ask me, I am going to throw this ball, it tells you where the rate of change is 0 in the function. That is one of its properties, but yes, exactly. So if I throw a ball down a hill and I tell you, like, I want to know, like, at what time that ball is going down, well, you kind of want to see, like, how fast it's going down, and then, like, you can get, like, an estimation of time, like, well, if it's going this fast, then it's going to get there at this time. So a derivative is just telling you a rate of change. And you'll see why this will become relevant slowly. But if you have x squared, so you see the derivative function is just this line. Notice how so from negative infinity to 0, this function is negative. That's because the function here is actually decreasing. And beyond 0, this here is positive. That's because the function's increasing. So in here we have a negative rate of change, and here we have a positive rate of change. And where that rate of change changes from negative to positive is where we have a minimum.
Yep.
And so this will become very relevant in just a moment. But before then, partial derivatives. So partial derivatives, like they look really funky and weird for notation sometimes, but
I wanted to include this video, Jose, that I saw for, I think I had sent it to you in the chat for like visualizing partial derivatives. I'm gonna go ahead and send it like later on today. You were gonna say something about I think it's 3 blue and brown. It's the one where they have like this like 3D function and it looks like a parabolic like sheet. And then it's showing you like the partial derivative, like what each line looks like as a partial derivative. You remember that one, right, Jordan? I mean, right, Jose? I showed
I
it to you.
think so. But
Yeah, I'll put that
you
in the
can
chat so you guys could see it. I'll help you visualize that concept. Or who knows, maybe I'll make it myself.
But partial derivatives are really just a way to measure if you adjust one variable, like how a function changes when you adjust one variable, keeping all the other ones the same.
Exactly.
So with a derivative, like here we only had x, like this is just single variable. But if you have multiple variables, which we will see, then you need to know how to get the rate of change of one variable with respect to with everything else. And so you're gonna hold all the others constant. So all the others are gonna stay the change, and you're just going to observe that one variable that you want to get the derivative of, right? So how does the input change if I nudge this input a little bit, leaving everything else the same? So consider just a quick example. So let's say you have you want to calculate the cost of like a taxi ride, and where d is your distance, t is the time waiting, and then your function in cost of dollars is going to be c of dt. So we have two parameters here, distance and time. And so 250 is just going to be like the base fare for you getting in. 175 is how much it costs you per mile, and 0.50 is just going to be like
Wait.
the amount of time waiting. So let's say you want to get the partial derivative of how distance changes with respect. So the change of cost with respect to distance. So you can see the partial derivative here is 1.75, which makes sense. So the cost here, if I were to change distance by some amount, it would change by a factor of 1.75.
Mhm.
You see that we're holding time and everything else constant.
Yep.
And so if you had the same thing, if you want to know how the cost changes with respect to time, you hold everything else constant and you see that it changes by this factor of 0.50. So I hope this gives an intuition of how partial derivatives work. Yeah.
Was that a helpful illustration, guys? Yeah. Okay. So
So back to gradient descent, now that we have that. So again, visualizing gradient descent for a single parameter. So if we have a parabola, right? Let's say that you start with a random initial value and your weights here. So let's say, your model is y equals, let's say, b plus wx. So let's say you start with a random like weight parameter. Well, your loss is probably going to, and by the way, cost and loss are interchangeable.
Yep.
So your cost is probably going to be quite high, but you want to move down to that minimum, right? So you can see that this function here is plotting the loss with respect to the weight, or how those two change. And so what you want to do is pick the best value of W that is going to minimize your loss, because that's what's going to give you the most optimal model. And so what you want to do is go down the gradient. So you can see that this function here is decreasing. And so what that means is as you increase W, your cost decreases here.
Yep.
So we want to move in this direction. And now in the opposite case, like if you were here, you would notice that if you decrease W, so if you're going this way, then that would increase until you get to your minimum, right? So actually one thing to note is the derivative here is actually negative. So like if you draw the slope of the tangent line here, actually negative, but you actually want to increase W. So you're going to see how the updates are actually moving in the opposite direction of the gradients. But we'll see that. But you can see how this is denoted, the partial derivative of W with respect to the cost. So a little bit of the mathematical derivation of gradient descent. So again, you have, by the way, can everyone see this? Like, I know like maybe it might be a little blurry or something. Can everyone see it?
I think would it help if I zoom in a little bit more? Yeah. All right.
I don't know if I can zoom in.
I think that's much better, right?
Okay. So you have your model y hat, which is our prediction, and then we have our bias term, and then wx, right? And then we know that our loss function is going to be this one, which is mean squared error, right? Now this is the one that I showed you before, and this is really like you can see we just plug this in here, and now we have this this definition in here. So all we did is plug that in. Everyone can see that, right? Okay, so now again, like how do you minimize a function? You take its derivative, you set it to 0, and you try to like solve for the parameters that are going to that are essentially going to optimize this function, right? So we need to take the derivative of this function. And right now we're just doing it for the weight. You'll see in the next slide, we'll have to do the same thing for B. But again, right now we just want to update W, holding everything else equal. So the bias is also a parameter that we can change. But in order to solve for W, we're just going to keep that constant for now. So if you take the partial derivative of the loss with respect to W, you can see you have to do chain rule first because this is squared here. So again, we have this outside function and this inside function. So taking the derivative of that, you just bring down the 2 and decrease that one by 1. So you can see here we just did power rule. And now we need to do chain rule in order to get the derivative of the inside, which is just going to be this term right here. So if you take the derivative of this, holding everything else equal, you can see that y becomes a constant, b becomes a constant, and all you're really having is w xi, where w is actually the what we're differentiating. So that derivative just becomes negative x of I. Oh, whoops. Does everyone see that?
Yep.
I know the notation might look a little funky, but it's
We're good,
actually
on
the thing.
we're good on the derivative inside, even though there's a summation. We understand that it's just simple chain rule. You have your product rule, your power rule on the top, and then you take the derivative of the inside, and then you just keep going down.
Ignore the summation for now. Just look at the inside.
Yeah.
You can see how this is no different than if you were to do like a chain rule in the previous example that we saw.
Yeah.
So then you just end up with this equation right here, which is x of I times, and then this equation in here. You can distribute this x of I, and then you have this resulting equation.
Mm-hmm.
And so actually, this is pretty good because now you can plug the values of x in here and w, and you can actually get you can get the rate of change
Mm-hmm.
for w with respect to loss. Now, again, for b, like you kind of just do the same thing. You see that we start off with like our mean squared error, but this time you're taking it with respect to the bias. So now this is the variable that we're differentiating, and these become constants. So you have to do the same thing. Derivative of the outside is you bring down this 2. This becomes a 1, and then you just have this inside function here. And you have to do the derivative of the inside as well. So when you do the derivative there, you see you're just going to get a -1 because you have this negative. Everything else is constant. This b is doesn't have any like coefficients attached to it. So it just becomes 1. So you can see this is just a -1. And then, whoops. And then you can see how we just have this resulting equation now, which looks very similar to the old one. You can see the other one is here.
Yep.
And then this one is there. I know like right now, this might seem like a little scary and stuff, but we if you have questions, we can definitely explain it more intuitively. Now, why did we go through this whole process? Well, again, it's because we want a way to update our parameters such that like if you start off with a random line, you want to say, how do I update my weight and my bias such that it gets a little bit closer to the optimal model? And so we performed those calculations like so. So taking the b because it's right here, for example. So the new value is going to be just the old value of b, and you're going to adjust it slightly. This alpha here is called the learning rate, which just says how much you can adjust it. I did want to include a visualization here that I forgot to include, but if you make the learning rate too high, you can actually diverge. So meaning your loss will just get bigger and bigger, and it's actually really bad. And if you make it too small, then it's not it's going to take a very long time to converge. So getting the learning rate right is actually very important. And so you want to multiply that by the gradient here. So the gradient is telling you in what direction you should nudge this old value such that you get a newer, more optimal value. So does this make sense? I understand we just went through like some math. Does anyone have any questions?
Jose, if you go to the next slide, we can show a little bit better what happens with the alpha.
Yeah, yeah. So these little steps right here, these things, is essentially like your learning rate. And now you can see we have a three-dimensional like little canopy here. But we're just plotting loss versus the bias versus the weights. And so you can see how updating the bias is going to have some effect along this axis. And updating the W is going to have some effect along this axis. And we want to see how that relates to the loss. So we get this 3D visual. And what gradient descent is going to try to do is roll this ball down the hill such that you get to your minimum.
Mhm.
And again, like if you were to take the derivative here, this would be an upward slope. So like it would tell you that the function's actually like increasing here, but we want to move opposite of that. So we want to go down.
Yep.
Because what it's telling me is if I was like over here at like 2, then my loss would be really high for W. And what it's telling me is if I want to optimize my W, then I need to decrease it. And so that's essentially what I need to do. You see the same thing here for the bias.
Which is why we have the negative alpha times.
Yeah, that's exactly. That's why in here you see a negative and not a positive. You might say like, well, just sum it up. If you sum it up, what's going to happen is, so if you're here, you have a positive gradient. And if you start summing it up, like you start moving away. So you'll start going away from the minimum. And that's not what you want. You want to move towards. So I know it might seem counterintuitive, but you're moving opposite the gradient. I mean, if you look at it visually, it is intuitive because like you want to go down. Yeah. I hope that makes sense.
I think that the visualization definitely helped, right? Yep. All right, let's go to the next slide.
Okay.
Oh, now we're going to the Colab notebook.
I have a Colab notebook to share with y'all.
You didn't put the link on it? Okay.
I did.
I thought you had put the link. It's,
Like the link?
yeah, for the Colab notebook. I'll put it in the chat.
It's in the roadmap. Yeah.
Do you guys have the link to the Notion? Yeah. Anybody here not have it? You don't have it? Are you in the AI guild? Okay, if you go, it's in I think it's in one of the pins. You'll see the Notion, and then it should show up there. If anything, I think I should do.
So
You got it? Okay, so everybody has it, I think.
Wait.
Everybody in chat have the notebook?
Shoot.
Okay, so Ed has it. Nice.
Yo, I think I'm missing some imports here. I don't know what happened. Where did my imports go? I was supposed to have some more imports up there. I think it's these though. I think these are just the ones I need. So let me
get to the notebook itself. Actually, notebook should be here.
Okay, I don't know why those just disappear from me. The first thing that I want to show you is actually this gradient descent visualization. Please, it will work. Okay, beautiful. So, yo, by the way, if you think I coded this up, you overestimate me. This was Claude. This thing cooks so much. So anyways, I just wanted to give you like an intuitive sense of like what happens here. So you can adjust this little slider, and you can see, by the way, this is just plotting the loss with respect to a parameter W. And so you can play around with this and see how updating the weight changes the loss over here. This little pink point is your next position after a gradient step.
Yep.
And then you can see like your loss function right now. So it gives you like a little bit of intuition, I guess, behind like what's going on here. So again, what gradient descent is going to do, it's going to adjust the slider a little bit such that it takes those tiny steps until you approach your minimum over here. So imagine that like you start off with a random model that, let's just say it's your model is just going to be like y equals, let's just say it's like -5w. Let's say that bias is 0 for now. Let's just hold that constant. Well, you see that your loss here is 27, which is not that good. You want to get to a loss that's lower. Although when we get to overfitting, you're going to see it's not that simple.
Where
What?
did you put the link to the notebook in the foundations in the Notion page?
In the Notion page? No, I don't know if it's in the Notion page. It is in the slide though. If you click on the slide,
Do you guys have the slides? Yeah, it's in the slides. It should go.
yeah.
It's in the slides are in the
And I'm going to put this on GitHub afterwards as well.
see the slide go.
Yeah, we'll share. For now, I just want to show like, so let's say you start off with, because at first we don't know anything about the data, like we have to learn it, right? So you start off randomly and you start off doing really bad. So you're like, okay, so where do we go from here? So you compute your loss, which you have it here, right? The loss with respect to W, and it's a -10. So what does this mean? It's trying to say, okay, let's adjust our W such that it goes against this gradient. So actually, you can see the calculation here. So let's say that our learning rate is alpha. So my value right now is -5. And this alpha is telling me how to like nudge it a little bit. So let's say I calculate my gradient to be -10. Okay, so now if I perform this this new update, so -5.
It's the first link now.
So -5, and then I'm having minus, and then this is 0.1 times -10. So this actually comes out to 1, right? But it's a -1, and then -1 times negative becomes a positive. So it's saying, okay, now increase W by 1. Okay, then I do that. And you start to see that if I increase W by 1, it was at -5 over here, and I get to -4. So now like I go to -4. And that's where my W is. So now I've moved here. And then you keep repeating this over and over again. So you see now we have this new update. So I calculate my gradient again. My gradient is -8 this time. You see like the slope starts to level out. And so the updates actually get smaller as you go. As you get closer, they just get smaller and smaller because the gradients get smaller and smaller.
Yep.
So you see, okay, now we perform this new calculation, and I want you to adjust it by a factor of 0.8, such that you have -3.2. And then, okay, we go to -3.2. And I hope that you're starting to get like an intuition of what's happening here with this. Does everyone understand this?
Yeah, everybody here's got it.
Okay, nice. I also have a 3D one, because, why not? What?
CM is not defined.
CM, bro. What is CM? Do I have a? Hold up. Give me a second. Give me 1 second. I got you. And the imports. See, this is what happened. I don't know what happened, but my imports got a little messed up. There we go. Okay, should work now. Demos, bro. Am I right? Sheesh. It's tough out here. Okay, so now we have a 3D version of it. So now, dude, it's crazy. 2D looks like, well, that's just a box. But 2D was like fairly simple. You know, like you just had this, and then the moment that you go to 3D, like, you know, things just like change quite a bit. So now, I mean, it is the same intuition though. Let's say that we start off with really bad weights and biases. So like they're all the way over here, although it's a little hard to see. That tip over there, I think it's -4, -4. I'll go on the opposite extreme because I think it's easier to see. Okay, everyone can see we're like at this little peak right here.
Mm-hmm.
And we want to move down because like our minimum is down here, right? So again, you do the same thing. Like you have to calculate the loss now with respect to W as we were doing before,
Yep.
and also with respect to B, because now you're not just changing, like you're not just moving in one direction now, you're kind of moving in two directions. So you need to move in the W direction and you need to move in the B direction,
Yep.
right? Because depending on, and by the way, you can see the contours down here, which helps out. This is like if you've seen a mountain map or something, like it's similar to that.
Yep.
So again, like you take the partial derivatives here, and you get your gradients for each one, and it's the same thing. Like it's gonna tell you how to move B and how to move W.
Yep.
So in here we can see the partial derivatives are both negative for W and B. And so when we adjust our new values, so it's like, okay, we need to nudge W slightly more. And so right now our W is -4. And we see we need to increase it a little bit to get to the minimum. So that's what it should be telling me here. Although that says negative. Oh, right. So the new value is going to be -3.2. So we adjusted it by 0.8. And so if we go to -3.2 and -3.2, -3.2 and -3.2, you can see that now we're slightly lower, like we're over here. And if we perform our next step, you're going to end up there. So you see we're like slowly moving down the hill. Does everyone understand this?
Yep.
Okay, perfect. I'm not sure if to just wrap it up there. I have some more things. By the way, don't worry about any of this. I don't even know what the heck is happening here. Okay, that's just plotting. What I will tell you, if you have some time, to go over the linear regression stuff over here.
Mm-hmm.
It's actually fairly intuitive. I have just a lot of graphing and a lot of things over here. But actually, that's just more graphing. But the main thing is over here. So you're gonna see like the model. Whoops, let me just scroll all the way to the top. By the way, if you've never seen object-oriented programming before, it's just like a neat way to represent your functions and things like that. So I made this linear regression class that has a learning rate and number of iterations. So this is useful because of gradient descent.
Mm-hmm.
And then this is simple gradient descent. So let's say we just have these two parameters, the weights and the bias. The rest of these things are literally, this is just for graphing, and this is just for gradient descent. So our model is actually just these two variables. And of course, to predict, we just multiply x times y plus b. So this is essentially just y hat equals like w times x plus b. So I would just go through this real quick afterwards, and then if you have questions, you can ping me.
Yeah.
But going back, So just a quick recap. What did we learn about today? So ML fundamentals, supervised versus unsupervised. Remember workflow, get the data, train the model, make predictions, evaluate and refine it. Linear regression, how can we use X to predict Y? Remember the general format is just Y hat, our prediction, and then our bias with our weights and our features. How do we measure how well the model fits? We use a loss function.
Yeah.
And in order to, optimize our model, we're gonna use gradient. So this here, these little nudges over here. So I does anyone have any questions on that?
No questions down here. It seems.
No? Is there no questions because you all really get it and you're all absolutely amazing at this? Or is there no questions because you don't know what's going on here? You can be completely honest with me.
Yeah. No, I think they pretty much got it. The
Okay.
visualizations definitely helped, in my opinion. Everybody's good here. Nice.
Lit.
Nice.
So if you could fill out a review for us on Google Maps, this would be great. No.
I think that could be a little homework for them to do.
Yeah, this is it right here. So I want you to try to fit a linear regression model on this Kaggle data set. So Kaggle is a machine learning platform that has a whole bunch of data sets. This is a super just easy, intuitive one. It just has these values that it's just simple linear regression, where you have the years you've worked, so years of experience and your salary, and you want to correlate years of experience with salary.
And I think by doing this, you could also fit this in your resume. Once you get this done and you get it predicting, you can add it to your resume that you created a little project where you predicted salary with whatever independent variable you have with years of experience. Yeah.
Yeah, and I can probably go over at the beginning of next class actually to kind of.
We could take a look at what you guys did basically in class, right?
What?
Like whatever they come in, I'll go ahead and take a look at their notebooks to see how it went.
Sure, and I'll go over it. Yeah. Next time on Dragon Ball Z. So next time, so for next class, we're gonna go over logistic regression. What's up, Jordan? What's up, bro?
Good.
Yo, congratulations, by the way.
Thank
So next time we're going over logistic regression. We're going over neural networks, and we're going over some more math, some linear algebra this time around. All right.
All right, guys, that's it.
I'm excited.
Yep, that's it. Thank you all for coming.
All right, guys, thank you.
All right. I hope you all got something. I hope this was useful to you.
Yeah, definitely. I like how you put the next time on Dragon Ball Z there.
Yeah. How do I stop the recording? Oh, there.